Imperfections in crystal structures. Introduction. Welcome to our video on exploring lattice defects, imperfections in crystal structures. In this presentation, we will delve into the fascinating world of lattice defects, also known as imperfections, and their impact on the properties of materials. So let's begin our journey into the hidden world of crystals. 1. Crystal lattice basics. Before we dive into lattice defects, let's understand the foundation, the crystal lattice. Crystals are made up of atoms arranged in a repeating pattern, forming a well-organized and regular structure. In a perfect crystal, this arrangement extends infinitely in all directions. 2. Types of lattice defects. Now, let's explore the different types of lattice defects that can occur in materials. Point defects. These are localized imperfections, including vacancies, missing atoms, interstitials, extra atoms, and substitutional defects, where one type of atom is replaced by another. Line defects. Dislocations are disruptions in the regular pattern along lines or planes in the lattice. Surface defects. Grain boundaries, twin boundaries, and surfaces/interfaces represent defects at the boundaries of different crystal regions. Volume defects, voids, inclusions, and precipitates are defects that exist within the bulk of the material. 3. Formation and classification. Lattice defects can arise during various processes, such as crystal growth, mechanical deformation, and phase transitions. They can be classified based on their dimensionality, which determines their impact on material properties. 4. Effects on material properties. The presence of lattice defects significantly influences the material's properties. Mechanical properties. Lattice defects affect the material's strength, hardness, and ductility, often making it more susceptible to deformation. Electrical and thermal conductivity. Defects can either enhance or hinder the flow of charge and heat through the material. Optical properties. Imperfections can alter a material's ability to absorb, reflect, or transmit light. Material stability and reactivity. Lattice defects can influence the material's chemical reactivity and stability, impacting its overall performance. 5. Importance in materials engineering. Materials engineers harness lattice defects to tailor materials for specific applications. For instance, intentional introduction of defects, doping, can create semiconductors with desired electrical properties or enhance the efficiency of catalysts. 6. Characterization and observation. Scientists use advanced techniques like microscopy, diffraction, and spectroscopy to study and observe lattice defects at the atomic level. 7. Future perspectives. As technology advances, understanding and controlling lattice defects will become increasingly important, opening up possibilities for novel materials with tailored properties. Conclusion. Lattice defects, while seemingly imperfections, are the hidden architects that shape the behavior of materials. Their study not only deepens our understanding of crystals but also paves the way for innovative materials with extraordinary properties. Thank you for joining us on this journey of exploration. Stay curious, and keep exploring the world of materials.